I know sometimes you need to define a heat flux and Abaqus itself is not enough. You are frustrated and the Abaqus itself is not enough. Be with us to tell you what to do. The solution is the Hetval subroutine. We will explain what it is, how it works, and how you can use it for your own simulation. Have you ever heard of heat flux? If not, let us define it. Heat flux is commonly defined as the amount of heat transferred per unit area, per unit time from a region of higher temperature to a region of lower temperature. The Hetval subroutine is developed to assist you in defining heat flux generated internally in materials. It removes the limitation of Abaqus in this matter and has various applications in industry. Did you know the applications of the subroutine? We will explain. Have you heard of phase change materials? Hetval is a low-cost, promising tool for modeling the heat generated during the phase change in these materials. Another use of the Hetval subroutine is to simulate heat generated from a chemical reaction, which is significant in various fields. Additionally, Hetval serves as a tool to model thermostress and deformations in metal alloys during solidification, covering the entire process of transforming molten metals and alloys into solid pieces. Furthermore, there is widespread research and practical application of Hetval to simulate the thermal behavior of fiber-reinforced composites. These are just a few instances where Hetval is employed to simulate heat flux, especially when Abaqus alone is insufficient. Hetval, similar to other subroutines, functions by collecting essential data from Abaqus at each time increment and point. It then computes the necessary parameters such as the heat flux and finally sends them back to Abaqus. But when can it be used? Are there any restrictions? Yes, it can only be used in Abaqus standard. If you are working in Abaqus Explicit, you can use the Hetval instead. However, in this lesson, we will concentrate only on understanding the Hetval subroutine. But if you want to read the manual yourself, you can check the Abaqus User Subroutine Reference Manual. Simply go to the User Subroutine, then Abaqus Standard Subroutines, and navigate to the Hetval section for detailed information. We have discussed how the subroutine takes data from Abaqus and sends them back. But how is it done? It is simple. We can easily link Abaqus to Hetval by adjusting the required settings. To do so, when creating a material, navigate to the Edit Material window, select the Thermal menu, and then choose Heat Generation. This will add heat generation to the material properties as shown in the figure. And now Abaqus knows that it should get heat flux from the subroutine for the material. Here we explore the interface for the Hetval subroutine. As you can see, the subroutine starts by defining its variables such as CM name, temp, and so on. Then we have included a file name aba_parm.inc, but what is that? This file contains the necessary definitions for Abaqus standard, where variables are set as 8-byte floats, resulting in a double precision floating point format. Abaqus automatically adds this file to your system when you install Abaqus, so we don't need to change anything here. Next, you will see the definition of a character as CM name. CM name is an 8-byte string variable that automatically stores the material name and must be a part of the Hetval subroutine. So till now we don't have any option to alter, and we can simply copy the required definitions from the Abaqus documentation to our subroutine. Then the subroutine determines the dimensions of arrays, which have been defined in the list of subroutine parameters. For example, temp is an array with 2 components. State V represents the user-defined state variables, and its size will automatically be called from Abaqus. Pre-def is an array whose dimension will be automatically passed in from Abaqus. Time and flux are arrays, each with two components. Deep-red is an array getting its dimension from Abaqus automatically, so still we don't need to change anything in the subroutine until this point. The main contribution of our work is writing the user code to define flux and user-defined state variables in the subroutine. Then the subroutine ends and returns variables to Abaqus. Flux is the only parameter that needs definition in the subroutine and will be passed back to Abaqus. It is an array with two components. What are they? The first component represents thermal energy per unit of time per volume in the material, denoted by R in this equation. This can be described as the product of density, denoted by ρ, specific heat capacity, denoted by Cp, and the derivative of temperature with respect to time. Specific heat is the amount of heat per unit mass required to raise the temperature by 1 degree. In this equation, ρ is the density, Cp is the specific heat, capital T is temperature, and the lowercase t is time. Flux 2 is the variation of heat flux with respect to temperature. We also have an array named state V, which is optional and can be defined within the subroutine only if needed. State V is an array representing user-defined state variables. For those unfamiliar with state variables in Abaqus, they can store material properties, damage parameters, or any other quantities that depend on the state of the system. We can define and update these state variables in user subroutines for every integration point and at each time increment as needed. When we use Hetval solely for an uncoupled heat transfer analysis, the last updated values of state variables at the start of each increment are automatically transferred from Abaqus to the subroutine. But what about coupled field analysis, such as thermal mechanical problems, where Hetval is used with other subroutines like USDFLD, UEXPAN, CRIB, UMAT, or UTRS. In these cases, our subroutines will be called before Hetval. So when we update state variables in them, the updated values in the increment will be passed into the Hetval subroutine. But in both the coupled or uncoupled analysis, the subroutine will pass back the updated state variables to Abaqus for the rest of the solution. So it is a loop. Hetval gets the last saved values for state variables in each increment from Abaqus or other subroutines, updated them based on the problem status, and sends them back to Abaqus to be stored for the next call. Now you know that Hetval provides the necessary information, allows us to update the heat flux and state variables, and then returns the updated values to Abaqus. But have you thought about how Abaqus takes the number of state variables? It is simple, you need to do it yourself. Simply, you can define it in the Edit Material window in Abaqus when you want to define a material. To do so, choose the General menu and then select Dipvar. Then input the number of state variables you need to be defined in the subroutine. Abaqus will automatically send it to the subroutine. If you are unsure where to start or how to write a subroutine, don't worry. We will guide you step by step in this package through practical workshops. Let's explore one of them. In this workshop, we will model a multi-layered carbon epoxy laminate called AS4/3501-6 prepreg. It is 2.54 centimeters thick with both length and width, measuring 10.16 centimeters. The specimen consists of 4 ply layers with equal thicknesses. The top and bottom layers are angled at 0 degrees, as shown in the figure, while the inner layers are perpendicular to the top and bottom ones. During curing, the specimen undergoes compression and heat as a result of contact with the mold. However, for this analysis, we focus solely on heat by solving an uncoupled heat analysis. Our aim is to teach you how to utilize Hetval subroutine in such a scenario. We will simulate the curing process, evaluate the degree of cure, and observe the temperature changes within the domain. Now let's see the material properties. Do you remember the thermochemical equation we wrote earlier? If not, take another look at it here. To solve this equation, we need all its parameters. Let's refer to reference 2 to extract the required properties. The composite has a density of 1,578 kilograms per cubic meter. Its specific heat is 0.1431 joules per kilogram per degree of Kelvin. Also, the total curing time amounts to 18,096 seconds. Thermal conductivity is 5.43 in the x direction, which represents the fiber direction, and 0.4137 in both y and z directions, measured it in watts per meter per degree Kelvin. These values should be defined for the material properties in Abaqus. HR, a parameter defining the total release heat during curing, equals 473,600 joules per kilogram. The fiber volume fraction represented by VF is 52%. The resin density will vary with the degree of cure according to this equation. It stabilizes at a constant value of 1,272 kilograms per cubic meter once the cure degree reaches 0.45. We also require frequency factors AI, where A1 equals 2.101 times 10 to the power of 9. A2 equals minus 2.014 times 10 to the power of 9, and A3 is 1.96 times 10 to the power of 5. All these values are measured in units of per minute. Delta E1 is 8.07 times 10 to the power of 4. Delta E2 is 7.78 times 10 to the power of 4. And delta E3 equals 5.66 times 10 to the power of 4. All these values are measured in joules per mole. Now let's outline the curing cycle that we need to apply. This covers everything you need to know about the definition of boundary conditions in this workshop. However, you might be wondering how to write the subroutines for defining the proposed boundary conditions and heat flux for the simulation. It is explored in this package. This covers what you need to write in the subroutine DISP and Hetval, which is the essence of this workshop. We have utilized the subroutine to solve the problem. Now let us describe the modeling procedure in Abaqus step by step. After defining the geometry, we define the material properties. Go to the property module and start by creating the material. First, click on the Create Material tool. Specify the density by clicking on the General menu in the Edit Material window, then select Density. The density is 1,578 kilograms per cubic meter. Enter this value in the provided field. We also have two state variables within the subroutine which need to be considered in the material properties. To define them, go to the General menu and select DIPVAR. Then specify the number of solution-dependent state variables, which in this case is 2. Next, let's define the thermal properties. Go to the Thermal menu, select Specific Heat, and then enter its value as 862. Then, in the same menu, select Conductivity to define the thermal conductivity values in the X, Y, and Z directions. So Abaqus can calculate how heat spreads within the material. However, the conductivity varies in different directions within the composite, but it has only one field here. So we select orthotropic option from the type combo box. First, enter the conductivity in the fiber direction K11 equal to 5.43. Then enter the values for K22 and K33 both equal to 0.4135. After that, select the thermal menu again and choose heat generation. Abaqus understands that it needs to extract heat flux information from the Hetval subroutine. We have defined other properties and step settings. Now let's instruct Abaqus to retrieve data from the disk subroutine. To do so, choose User Field option from the distribution combo box. Enter a magnitude of 1 which will be multiplied by the values defined for U1 in the subroutine. Finally, click OK to create the boundary condition. Now let's explore how to view the temperature history at the central point which was saved using the history output. It is straightforward. Click on the Create XY Data tool, select ODB History Output option and then click Continue. Then ensure that the temperature output result is selected and click on Plot to plot the temperature over time. You can click on the XY Data Manager tool and then click on Edit to copy or edit the results. For example, you can copy this data, paste them into another software and then compare them with the reference solution. Now click Create button from the XY Data Manager window. But now select ODB Field Output instead of ODB History Output and then click Continue. Select Unique Nodal option from the Position combo box and then check STV1 to save cure degree. Now click Plot Undeformed Shape tool to plot the composite again. Then go to the Elements Nodes tab to select a specific point where the cure degree needs to be extracted. Now click on Edit Selection and select a point located on the exterior face toward the y-axis at the middle height of the composite. We select this point just for verification purposes against the reference solution. Now click on Plot to visualize the cure degree over time. You can click XY Data Manager and then click on Edit to copy or edit the results if needed. We have copied the temperature and cure degree data from Abaqus and exported them for verification with the reference solution. As you can see here, both the temperature and cure degree results are well confirmed with the reference solution. This covers the essential steps to model the curing process in the fiber reinforced composites using Abaqus. We hope this workshop proves valuable for your understanding, as it was a semi-real problem. However, the curing process in composites is complex, involving the consideration of temperature and mechanical fields simultaneously. But we have simplified it here for you to learn how the Hetval subroutine can be applied in a real example like curing, which is a well-known process. Well, that's it, people. If you need more information, you can buy the full training package to learn the details about this subroutine. We hope the lesson has proven to be beneficial for you. Have a great day and goodbye. Hello everybody and welcome to our new video training package of Abaqus. Hetval subroutine in Abaqus. Looking to learn more about how to define your own heat flux due internal heat generation? Check out our new package. In this video, we introduce you to the package that explains the intricacies of Hetval subroutine that helps you in simulating heat fluxes when you have internal heat generation. We'll also show you how the package examines this subroutine in a real-world example such as curing process, giving you a comprehensive understanding of the entire process. Whether you're an engineer or just curious about the topic, our package has something for everyone. Don't miss out on this opportunity to expand your knowledge and improve your skills. This package includes these sections: Lesson 1, Introduction to Hetval subroutine in Abaqus. Workshop 1, Simulation of a 2D domain under constant heat flux. Workshop 2. Simulation of a problem in which heat flux depends on time. Workshop 3. Simulation of a problem in which heat flux depends on temperature. Workshop 4. Simulation of a problem in which heat flux depends on a state variable. Workshop 5. Simulation of the curing in a prepreg laminate. Lesson 2. Simulation of the curing process in fiber-reinforced composites.